Welcome to Analytics Learning Series at AWS. This is Dipankar Kushari. I'm a Senior Analytics Solutions Architect with AWS, and today I'm going to talk about and show you how you can use Delta Lake on Amazon EMR to easily maintain ever-changing data in your Amazon S3 data lake. I'll also show you how you can analyze Delta Lake data with Amazon Athena and Spark. As you might have already experienced, moving your data initially to your S3 data lake using bulk load operations is quite easy. But as your data keeps growing and changing over time, keeping that data fresh, up to date, and accurate in a scalable manner is not. You do not only have to take on the burden of managing and updating files in your data lake yourself, but also need to devise a mechanism to snapshot, restore, or roll back specific changes as necessary when trying to troubleshoot and solve problems resulting from poor data quality in upstream systems or logical data corruption. As data privacy regulations began to go into effect, it required companies that store and process user data to provide users with the ability to remove their users' data on demand. This is more commonly known as the right to be forgotten. This represents a difficult challenge for data lake to read, modify, and then rewrite those files in order to comply to user requests, which can be very IO intensive process, as large data sets often need to be rewritten just to remove a few records. To address these challenges, Delta Lake was created that provides transactional guarantees and enables schema enforcement and evolution. Delta Lake is an open source storage layer that brings reliability to data lake. It runs on top of your existing data lake and is fully compatible with Apache Spark APIs. Delta Lake offers ACID transactions on Spark, upserts and deletes, scalable metadata handling, schema enforcement, time travel, and unified streaming and batch data processing. Here is how a high-level diagram would look like. As your raw data is ingested into your data lake, you will process those files and save the files into Delta Lake storage format. EMR with PySpark is used to read and process this data. A glue data catalog table is created on the Delta Lake storage on S3, and then we can query it from Athena. We can also query this data using Redshift Spectrum after we create an external schema for Redshift Spectrum pointing towards the glue data catalog database. AWS Lake Formation will be used to control accesses to the database and the tables created during the process. We will use a simple JSON data generator to perform this demo. It simulates a trip information where each record has a trip ID that acts as the primary key. Route ID can have 10 different values and used as partition key, destination, timestamp, and origin. We will use a EMR notebook to demonstrate the following using Delta Lake. We will create a Spark data frame from synthesized trip data, save it in Delta storage format and create Spark table, create a table in Athena, query the data in Athena and Spark SQL, delete, update, and insert data with schema evolution, query updated data, and finally we will perform time travel queries. So without further delay, let's go to the AWS console and show you how this can be done. I have already provisioned a EMR cluster which is having Spark, Livy, Jupyter Hub, Jupyter Enterprise Gateway, and Hive. And there is also a EMR notebook that has been created and is associated with this cluster that you just saw. Now, this cluster with this notebook is already up and running. This notebook I have already started. One thing to note here is the package. this package is required is part of the configuration for Delta Lake to work. You'd also need to set these variables and configuration. So here I have imported the Delta tables and also set up two paths on S3 location. So let me show you the S3 location. This is where currently you see only input jar and output, but you will have more folders getting created. This is where our Delta Lake or Delta storage format files will be stored. So let me go back to the notebook. First thing we will do, we will define the methods which will actually create or synthesize the data. So let's do that. Now we will create a Spark data frame from the trip data. So here I have created a list, Python list, which is having these values. These are destination values. And then I will call this method here, the get JSON data and create JSON DF, and that will create 2 million records. So it will start from 0 and it will create 2 million records. Let's do that. So the records are getting generated and data frame will be populated. Okay, so it is done. This is some sample record. So this is the column that you have for this data frame. We can also look at this if we do the print schema. So this is how the schema looks like. And as it shows, it has df1.count. So it has 2 million records. Now we have the data frame df1, as you saw here, df1. Let's save it in Delta Lake format in S3. So let me again show you the S3 location. You will see that the files will get created here. So let me go back to the notebook. Again, I would like to highlight that we are going to save it in the Delta Hype path, which is basically inside the Delta, we'll have a demo video and then we'll have a prefix Delta Hype table. The Delta Spark path will be inside demo video inside Delta, and then it will have a separate path, Delta Spark table. I just wanted to show you, or I will be showing you, that you can create both Hype table and Spark table, and you can actually access the Hype table from Athena. So let's create the files in Delta format, and we will partition it by route ID. Route ID, as you can see, this is the route ID. As I was saying earlier, there will be 10 different values, so A through J, and it will keep repeating. That's how the process works. Basically, it is this process that creates 10 different route ID, as you can see here. So let's go and save the data frame in S3 in Delta format. Again, highlighting the Delta format. So it's getting created. Let's go to S3 and let's refresh this. As you can see, it has created the prefix demo video inside this Delta Hype table, and it's going to create the folders or the prefixes with the Hive-like partition. So if I go back here, again, see it is saving in the Delta Hype path. Okay, so this is done. So if I go there, I will see 10 different folders or prefixes. A through J is created, and we have the files created. It's actually in Parquet format and compressed in Snappy. So now we can start reviewing this data using Spark SQL temporary view. So we are reading the file that were created in Delta format. from that path, and then we are creating using the Spark create or replace temp view and calling the table as a temp trip table. So we are going to run some queries, like we are going to do a count, we are going to perform some sample data, and we will look at the maximum trip ID. Again, the trip ID is basically a auto incremented number that starts from 0 and goes up to 1 less than 2 million, because it is starting from 0. So let's run this. Okay, so first query was count start, so I can see that there are 2 million records. And remember, again, this is not being read from the data frame that we created earlier. This is actually read from the S3 location where the data was written in Delta format. We are reading it, and then in a temporary table in Spark, we are our view in Spark, and we are reading that and writing it here. This is some sample data. San Francisco is obviously one of the destination values here, which got created, and I'm seeing it here. And then the maximum trip, as we were saying earlier, 1 less than the 2 million. But if I go in Athena, so let me show you in Athena. So if I go in Athena, I wouldn't see any table yet. For that to happen, I have to create a manifest file, and we'll soon see that how a manifest file look like. But before that, I can actually create the table. Now see, the table is looking at a location which is called symlink format manifest, and you will soon see why I am doing that. Also, one thing to highlight is the SRD, serializer, deserializer, which is a Parquet Hive SRD, but the input format is a symlink text input format. So this is a specific format that you have to give when you want the files which are written in Delta Lake format to be read from Athena. And the output format is again Hive output text format. So this is created with the same columns, and then it's partitioned by route ID. How the partitioning scheme is followed in while saving the files in S3, as I was showing you. Let me go back to S3 just to make sure that you remember that. So see Hive-like partition based on route ID. So in Athena also we are following the same Hive-like partition with route ID. So let me create the table. Yeah, it just said that only one SQL is allowed at a time. Since I have two, I didn't select one, I just selected now, and the query is successful. So now the location is still not there. Remember, I have Delta Hive table. I still don't have this. So going back to the notebook, you can see the way you will do it is you will create an object called Delta table from that path, which is Delta Hive path, and then you will generate this manifest file. So let's run this and see what happens. So it is now successfully run. So if I go to S3, see, let me refresh it and see what happens. So I see that another prefix symlink format manifest is created. And if I go to Athena, this is exactly what I have selected here, symlink format manifest. So going back here, see how the Hive-like partition is created inside that as well. Basically, each of these partition creates a manifest file, and let me show you what that content of that manifest file is. So if I run this query, you will see this is nothing but a text file which actually has the list of files or Parquet files in Snappy compressed Parquet files, which are created and stored in the actual Delta storage format under Delta Hive table. So if I open another tab here for S3, and if I go back and go inside route IDA, so you will see that this has this file which is 7028 and 49AC. So if I go here inside the manifest, again remember I'm inside the manifest folder or prefix with the route ID equal to A inside that partition, and see here it has A7028 and A49AC. So basically it is giving you all the list of files that Athena should read when it has to read that table. So now that this information is created in the manifest, what I need to do next for the files to be available or the data to be available, I need to do a MSCK repair table so that the partition information is updated. So if I go in the glue console, you see I am inside the demo delta DB and already delta trip table is showing up. And this is what the delta table looks like. And if I look at the partitions, I just now created this partition. So these files are pointing to those manifest files, as you can see. As I was showing you, in this case, I clicked on the partition H. So that is what is showing up. So going back to the notebook, EMR notebook, let's also create a Spark SQL table or the Spark table, right? So we already have the database. Now remember, this was a temporary view or table in Spark, but I am now talking about creating a table in the Glue data catalog, which is more like permanent in nature. It's still an external table. So this demo delta DB is the database in the Glue data catalog, as you saw, demo delta DB. So I'm still creating a Spark table over there. And in this case, what I'm doing, I am actually using the save as table option, and I am saving it in the Delta Spark path. So if you remember, I mentioned this at the very beginning that I am also creating another variable called Delta Spark path. Now it goes under the demo video, but it goes to a different prefix. So Delta Spark table is what we will see getting created inside the S3 location. So if I go here and under demo video today, I only have Delta hype table. So now once I run this, you will see that I also have that location created. I will also have, so in the Glue catalog today under demo delta DB, I only have one table. But once I create that, you will see I also will have a Delta Spark table. But I cannot access it from Athena because you just saw to access from Athena, you need to create that manifest file. But I should be able to access this table from the Spark using the Spark command or using the Spark API, right? So let's save it again. This is in Delta format. It's again partitioned by route ID. It's going to be saved in the Delta Spark path, and it is going to be saved as a table, which will be called Delta Spark table. So let's run this, and then let's run that. So once it is created, if I go back to the S3 location, remember I only have Delta hype table. Now you see I have Delta Spark table, and again it is partitioned by the route ID, and it's written in Delta format. So it's done. So now if I look at the tables that I have in the demo delta DB, I see three of them, right? Two of them are permanent and one of them is temporary for this session in the Spark. One is the Delta Spark table, another is the Delta trip table. Okay. Now let's look at the DDL for the Delta Spark table I just now created in the Spark. So this is how it looks like. And let's query some data from the Delta Spark table. We are using Spark Magic here. So the output will be written into the Delta trip op. And first query we are running is the same queries, select count star, and then we are doing a max trip. And then we are getting 10 records, and finally we are getting the distinct route ID. So remember again, this is from the delta spark table, right? So let's do that. So again, you can see there are 2 million records. And then the max is obviously one less than the 2 million. These are some sample records. And again, I have 10 different route IDs, right? So let's run the same query, but this time we will run it against the delta trip table. Let me refresh this. So you will see two tables shows up, but we can only query delta trip table from here. So let's run similar queries from here, right? So let's do the select count star first. Remember, we are running this on the delta storage format inside S3 that is stored as delta hype table. Inside that it is again partitioned using the hype type of partition, and then I am getting 2 million rows there, right, in the delta trip table. Let's do some similar queries that we did for the delta spark table. So here you will see that I will get, actually this should be trip ID, not route ID. Obviously up between A and J, A is the highest, so J is the highest, so we are getting J over there. But in this case, trip ID is one less than 2 million. Then I'm getting some sample data. In this case, I'm getting New Jersey. If I run it again, by the nature of how database works, now we are getting Seattle. Last time we got New Jersey. And then let's look at some of the distinct route IDs. So here again, I should be getting, so it's exactly giving you the same result. So just wanted to show you that. That's why the purpose of creating two different tables in two different locations. But this point forward, we will only be using the Athena table. So the first thing we'll do, remember our whole purpose was to perform some insert, update, delete, basically CDC operation. Delete is very important, especially someone requests you to delete their data on certain IDs. You should be able to do it without any problem. So that's what Delta Lake is your savior here. So first thing we'll do, we will insert some new records and we will use a schema evolution. So let me explain you that. So far, if you have seen the schema for the data frame or the table that we are using, it has route ID, trip ID, timestamp, and destination. Now we are going to add a new ID, a new column called origin. So in the origin, we will add some values here while we create the data frame. And what I am trying to show you is that as your time passes by, your schema could evolve. And even when your schema is evolving, if Delta Lake has the ability to handle that, and it can actually not only append the data, but it can actually append the schema. That means it can update the schema. So basically what I'm doing here, starting at 2 million, again using the very similar concepts here, creating the JSON. But in this case, I'm just using a new column called origin. So I will add origin as well, which was not there in the previous case. So along with the destination, you will have origin now. And I'm just adding 20 records. So starting at 2 million, remember my maximum was one less than 2 million. So I'm starting at 2 million and I am actually appending or inserting 20 new records with origin being a new column, right? So let's run this one first to define the additional methods, and then let's create the data frame. As you can see, I am actually, let me do a print. So it will show up here. Yeah, so you can see 20 records, and then I have these records. These are created. This is the data frame, right? Trip updates is the name of the data frame. So if I do a trip update dot print schema, you see that now I have something called origin, which was not there earlier. So again, I am going to save it in the delta hype path. And I'm going to save it in delta format. I'm going to use the mode append. Earlier, so far I was using override. So this is a new mode append. And the thing that is of interest here is the merge schema. So this merge schema option actually takes care of evolving schema or evolution of schema. And again, it is partitioned by route ID. I'm saving it in the delta hype path. So let us do that. Okay, so this is done. That means I have some new records that has been written, right? So this data has gone into A. So if I go to S3 and if I look at delta hype table inside route A, I see that new data has arrived. So this 1838 data is what has been added newly. So it's 1839 right now, which is just few seconds back it was written. So these are the two records which has been written in two files. Interestingly, if I go to the manifest, so let me go to the manifest, right? Because for Athena to show you this new data, it still needs to know where to read it from. And if I look at the manifest currently, it still shows only two entries. So manifest doesn't know that there is a update. But here there are actually, I'm still looking at the partition route ID A, there are actually 4 files, per K files. But here I'm still looking at route ID A, I have only 2 files in the manifest. So if I go to Athena, actually before that, let me query it here. So this has been created, this data is created, and then let's query the updated data here. Again, the same concept, we are using the temp table here, and we are doing a count start. So ideally 2 million plus 20, that's what we should see in the count. And that's exactly what is happening here. And just to show you some sample data beyond this, if I run this, I should see this new data. So this is up to this we had data. And as you can see, the origin was not there. So it is coming as null. And then all the new data where the destination is Syracuse. And this data has been created, and you can see the difference in the timestamp, right? So it was created at, these are all UTC times, so 23 on 11th March 23:19. Now this data, as we were talking, time passed by, and it is now 23:37. So that's when it got created. But if I go to Athena, so let's do a count star, right? First thing. So it still shows 2 million. So that's 20 because the manifest file, as I was showing you, is not updated. That's why it doesn't know about those files and it still thinks there is only 2 million. So no new records added, right? So let's update or generate the manifest file, basically updating the manifest file in the same location. So once this is updated, now if we go here, and if we go to manifest, and if we query the same file, you see now it has been updated with 4. So basically it has now updated all the files that is there under this partition. Same thing happened for the other partitions as well. So this job is done, right? Now if I go to Athena and run the same query of count star, now it shows the updated one. So it has the information now updated. Now let's do some update and see how the data can be easily queried. And once it is updated, it can be easily queried using the delta. First of all, just by using one command, you can update it just like you do in RDBMS, and then you can immediately query that updated data. So again, you are creating a delta table object for that path. And before I update, I just want to show you again using that SQL temp table or temp view, I just want to show you that what is the count for Syracuse, the number of records that we have where the destination is Syracuse, and then the number of counts that we have where the destination is Philadelphia. So if I run this query, you should be able to see the count. As you remember, I just added 20 records for Syracuse, so that's exactly what it is showing. And then there are 200K records for Philadelphia. So our objective for this update is for all the destination or all the records where the destination is Syracuse, I will update that using Philadelphia. So that means any destination that has Syracuse, it will be updated with Philadelphia. And I just need to fire this command. And at the same time, since I want to get that same information from Athena, this time I am actually taking care of updating the manifest file for Athena in the same at the same time. So let's do that. So it's done. Now let's run the same queries, exactly same queries. How many records are there where the destination is Syracuse and where the destination is Philadelphia? Now you see immediately it changed to 0, but says 220, 200 plus 20, right? 200K plus 20. So immediately the update is now done. And if I run the same queries in Athena, I should be able to see the same results because now I have already taken care of updating the manifest file. So I just need to change this to the Athena table. So let's run this. So it should show 0 right away. And as we were saying, it is showing 0. Going back here, I just need to change this to Philadelphia for Athena query. And here, let's run the query again. And it should say 200K plus 20. That's exactly what it does. So it's now consistent when I'm querying from Athena or from SQL. So let's now show you some delete queries. And this delete is very important as we have been telling because of the Data Privacy Act and all these things going around. So right to be forgotten, right? A customer comes to you, they say that I don't want you to keep my data, so make sure all my data. So you get data is deleted, so you get those IDs or somehow you identify that customer using some mechanism, and then you have to go in your data lake and delete that. So again, in this case, let's say whatever data I have for New Jersey as the destination, I want to delete those. So let's first look at the total count. And then we will look at the New Jersey count. So New Jersey count is 200K and total count, as we know, is 2,020,000. Again, it's a simple one line that you want to do. Just give the predicate, and then it will delete those records which matches that predicate. So let's run that. And let's query the same data. If I run the same query now, I see that there is no data for destination New Jersey, and also there is 200K records which are less compared to this. Now let's do some upsert. So upsert is when you already have some data and then you get the data based on the same primary keys. Certain times you get an update and then you also get some new data which you have to insert. So the data that has come now is actually an updated, some certain columns might have got updated, but the primary key is matching. So whenever you have a matching primary key, you update that those records. When the primary key is not matching, then you insert. So that's basically how a lot of these CDC operations work in ETL world. So this is how we will do it. Trip ID is our primary key. So using trip ID as the primary key, we'll merge it. And then when you matched, you update all of them. When not matched, you insert. So that's basically it. First, we are creating some records. Now, to do that, I have to create a data set or a data frame where I have some matching trip ID and some non-matching trip ID. So first, I had to look at the maximum trip ID. So maximum trip ID is 2,019,000, and then I went back a little bit. So I took all the trip IDs where it is greater than 2,014,000. So that means I have 5 overlapping. And just to show you, this is how the data looks like for anything greater than 2 million up to 2,019,000. So basically 2,015,000 through 2,019,000. It's all destination is Philly or Philadelphia, and these are the origin, right? So I'm creating a data set starting at 2,015,000. Remember 2 million beyond 2,014,000. So what will happen if I create 10 records? Then I will have these overlapping 5 records, which will have the same trip ID in this data frame, trip updates 1. And then I will have 5 more records which are not present today in the actual delta table. So I will have starting from 2,020,000 through 2,024,000. So let's run this. And as I said, so I will have up to 2,024,000, 2,015,000. But the interesting thing is, look at this data frame. Instead of all Philly being the destination, now I have this different destination, right? And then I have origin also changed all to Seattle, just to show you the difference. But the trip ID remains same because that's my primary key. It has to be same. And obviously, this is 2337 on 311, but now this is 312 at midnight, 33 minutes past midnight, right? So again, we will merge this as I was explaining. So let's look at this. So first of all, we create the delta table object, and then we do a delta table. We alias this with T. So that means this is my existing table. So this has data from 2,015,000 to 2,019,000. And I am joining on trip ID with the trip updates 1 data frame, which is the new data frame that I created, with which I am going to merge. And when it is matching, it will update. So that means everything that matches will be updated with this data. And when it is not matched, then it will be inserted. So I'll have this data inserted. So let's run this. Okay. So again, I'm reading from that delta hype path, but in this case, I'm just going to print everything beyond 2,010,000. So let's look at this. So notice the change. So up to 2,014,000, everything is still Philly, the destination. But starting from 2,015,000, where it actually matched, from 2,015,000 through 2,019,000, it has now changed completely. The origin is Seattle. So if you see here, 2,015,000 to 2,019,000, this was the data earlier, right? Now, if you see, the destination has completely changed and it got updated. Also, the timestamp, which is very important, just to show you that it is actually getting updated, I use the timestamp field. So it is getting updated. And then we have these 5 new records that got inserted up to the 2,024,000. Right? So this is how you can do upsert. Also, I wanted to highlight that you can do some time travel queries. So what does that mean is it keeps all the variations of this table as time passes by. You are making changes to the table. It keeps these. So the way you will read that is by using this history. And you can select certain metadata from the table, and let's look at it. So it will show you all the versions that the table has gone through. It starts from the 0th version and then it increments the version number. It also shows you as of timestamp what that version was relevant as of which timestamp and what operation was made to create that version, and if there is a predicate that is important or that is relevant, it will show you that. So for example, first we created the table at the very beginning and the mode was override, and we partitioned it by route ID. Then if you remember, we appended 20 records and we still partitioned it by route ID. Then we actually updated the table, right? And finally we deleted the table with New Jersey data getting deleted. When we updated Syracuse data with Philadelphia, and then we did a merge. So it shows you all these operations that has happened. And I can actually access this different version or checkpoint or image, whatever way you want to call it, of this table by using a timestamp as of or even a version as of. So if I do a timestamp as of now, when I previously ran it, this is a timestamp which is before actually the table got created. So let me first show you what happens if I try to run it. It's saying the provided timestamp, whatever I have provided, right? 170446 at 3/11/2021 is before the earliest version. So that means it is even before the table got created, right? Or the Delta files got saved. So let's copy this timestamp and let paste it here so that it can actually be queried properly. So if I query it now, so now what I have done is I have created a data frame by reading that specific version of the table, and I called it df underscore v0. The purpose of this is to show you that at that specific version, you can only query or you can only see whatever that version looked like, right? So for example, it had only data up to 1 less than 2 million. Remember first when we created 10 million, right? Or rather 2 million records. So if I run this now and try to see anything beyond 2 million, there was nothing in that version, V0 version, there was nothing, right? So it shows that there is no data. Now let's query the version 2. So version 2 is when I will have 20 more records than 2 million, but I will have updated the Syracuse data with Philadelphia, right? So again, the same concept I am reading, but in this case, instead of using the timestamp, I am using version as of. So if I do that and create the data frame df underscore v2, so this is a specific version 2 of the table, which has been loaded into the data frame. And if I run the same query, beyond 2 million. Now I see, because it was updated with Syracuse was updated with Philadelphia, I have all this destination as Philadelphia, but I do have records beyond 2 million, right? And then again, if I create two different data frames, Spark data frame, one is for version 1 and then the other one is for version 3, I can actually see sample data there, and we can see some interesting facts here, right? So if I, for version 1, if I do a Syracuse versus Philly count, I can still see 20 and 200K, right? Because it was still not updated. Syracuse was not updated with Philly. So I can still see 20 and 2 million, or rather 200K. But if I now query the version 2 table for the same exact predicate, which is destination Syracuse and Philadelphia, I would see that Syracuse got updated in version 2. All the records of Syracuse got updated with Philly. So these 20 got switched here. And then for version 3, actually let me call it version 3, right? No, this is version 2 is fine because I still want to see how the data looked like before the New Jersey data was deleted. So this is fine. So you can see there were 2,020,000 records and there were 200K records for New Jersey. Now in version 3, let me also go back and show you just to make sure you understand here. So version 2 is only the update, and in version 3 only, that particular version I deleted the New Jersey record and that particular version got created. So you can see the operation was deleted. So when I queried version 2, right, then I still get New Jersey record, 200K records and 200,020,000 records total. Now if I query this, I will see that I have no records for New Jersey and I have 1.8 million and 20 records overall. So that's how I can utilize or kind of take advantage of the time travel, get back those data by querying the data using time as of or version as of. And that's a very handy way to kind of roll back if I need to, or kind of get a view at certain point in time whenever certain operations have happened. Also, I would like to point out that what you need to do to get this set up, right? So you saw how I have set up the EMR and the EMR notebook. Just to make sure you can do it yourself, let me show you what you need to do. So just cloning of these, and then I can show you. So when you create the EMR cluster, make sure that you have Hadoop, you have Jupyter Hub, you use Hive, you use Jupyter Enterprise Gateway, you have Spark, and you have Livy. I have used the latest EMR cluster, so you can do the same. And then you can use Hive table metadata and use Spark table metadata. For both of them, you can use Glue Data Catalog. Okay? And then make sure, the other thing I must mention, you can use any cluster if you are just going to use the same type of data. 2 million is not a big deal. You can give any name. You can put some location where you want to keep the log files in S3. If you are not using a custom AMI, then you can just make sure you have a EC2 key pair, because if you really want to log into the or SSH into the master node, then you can use EC2 key pair to do that. And you can use the default security group for master. I'm not, and code and task nodes. I'm not going to create this. So make sure your clusters are available and accessible before you try to log into them. So once you do that, then you can create a notebook. So you can go here. You can give a name, you can give a description, and then once your cluster is up and running, you can actually choose that cluster while you are creating the notebook. And you can use a default security group, and a default role also is fine. And then you can create the notebook. Once your notebook is created, let me cancel it here. Once your notebook is created, if you click on that, and then you can just do a open in Jupyter. So that's what I did. And then in the Delta Lake, let me go to the top Delta Lake notebook. I created a Spark session. Then I configured this, right? As I said, this is very important. So make sure you configure this jar, and then when you do this, right, it actually creates or downloads those jar. If you are running it for the first time, then it downloads it into that. So let me actually show you by SSHing into that location. So this is the IP. Let me make sure I'm accessing the right cluster here. Now it has connected to the EMR, cluster. So I have SSH'd into that. And let me clear it. So if I go into, not this one, not this one. So if I go here, let me just quickly open up. Give me 1 second. Yeah, info.txt. So I just wanted to show you where these jars are located. So if you are doing it for the first time, this is where the jar files will be downloaded when you run that configure. So you see, this is where the jar is. And you can actually use PySpark command also to get into that. So the way you do that is like this. So if you do this, you can get into the PySpark and you can actually access it using that. So it is also looking for those 8 jars. It downloaded 8 jars because it is now getting downloaded in a different location. For PySpark to access it, it actually needs a different location. So this actually got downloaded in here. So if I go in the top, you will see that it says home Hadoop .iv2 cache. So this is and sorry, home Hadoop .iv2 jars. So this is where it got downloaded, right? So if I do a quit and if I do ls minus ltr, so this is where your jars are getting downloaded. You can also save it in a PySpark file, like a Python file. Yeah, here. So you can actually save it in a Python file and you can even run it as a Python file. So you can pass this as an argument and then you can run it, right? So in this case, you are going to use Spark Session configure like this. You will configure this like this, and then you can actually call this PySpark. So you can use Spark submit and then you can pass the packages and then you can give the file name, which is the Python file, and then you can, as you have seen probably here, let me again open it to make sure you understand. So here there are 2 arguments I am passing, right? Source path, where the files are, if you are reading from an existing file instead of a data frame like we did by formulating some JSON data, right? Or synthesizing some JSON data. If you are reading actual file, let's say in CSV format or some other format, and then saving it in the delta format, so you can basically say a source path, like in this case here, a source path as an argument, and then the delta path where you want to save it, right? And then pass the delta path. So there are several ways you can do it. I just showed you using the notebook because that's one of the easier way to run it. But you, as I showed you, you can do it from the PySpark. You can do it from within a file and then calling it. So if I go here, yeah, let's do a Control L. So first thing I'll do, let me go back here and open the Delta Lake. So let me see if it is going to be able to import that. So it's imported properly, right? So let's actually set this delta high path and let's just show you how you can run the same query over there, right? So the table is already there. So if I just do this, I should be able to run the same query from here. Yeah, it's just reading that. So let's do a count start. So at the end, we got like 1.8 million and 20, right? So I should see the same thing here. Actually, I think we got 1.8 million 25. Let's see. Yeah, I think lastly we added another 10 records, right? Beyond that. So the latest version is version 4. So that's what we should be doing. So let's do a version 4 and see here. Because last week queried version 3 where, so if you remember at the very end we did a merge, and in the merge we updated 5 records and we added 5 records. So that's why we are seeing that 1.8 million with 25. So let's do that. So version 4 is the latest one, version as a 4, and then let's run it. Okay, and then let's do this. We'll just need the count star overall count. So instead of that, we'll do a version 4 and then here a version 4. And yeah, making it version 4 definitely would help. So it's matching, right? So that's the latest. So if I do the same thing here just to make sure that we are on the same page. Again, remember version 4 was March. So just to make sure we are doing the same thing here, let's just do that. So we are doing that, and then we will do this. So again, trip table and then temp trip table. Because we were doing a version 4 here on the data frame version 4, that's why we got that. Now we should be able to get the same result here, right? Same. So version 4 is the latest. We are getting these many records here also. We are getting these many records. Going back to the console here. So the shell shows the same thing. So that's about it. I think we will end this session again. My name is Dipankar Kushari, and thanks a lot for joining me today.